Okay, so welcome everyone. Our first speaker today is Professor Suresh Nayak. Suresh will be speaking on Verdier and Grothendieck duality. Yeah, over to you, Suresh.
Okay, thank you. Yeah, so this is my last lecture, and I'll try to cover as much as I can. I'm not sure how much I'll reach. I still could not write everything that I wanted to write. So again, the last part will be live writing. Let's see. So, so let me just begin by recalling what we did last time. So we looked at Serre duality for projective space, and this was done essentially. This is sort of an argument by explicit calculation. So you start with a coherent sheaf, coherent OX module, and then one shows that the ith cohomology of F and the n minus ith cohomology of F to nth cohomology. So there's some sort of a cup product kind of thing, but one can explicitly say what this is. There's a map from here to Hn, and then this is isomorphic to A. And I forgot to mention, but it turns out that these are all finitely generated modules. So that's where F being coherent comes into play. So these are all finitely generated A modules. And one first checks it. Actually, what I said last time was only for, I mean, I mentioned it. So one proves it for OX A kind of modules. And then one sort of uses the fact that you can always project sort of a free module like this onto F, and I mean at the graded level, and then for the graded module, and then you can use that to find a resolution like this, and then somehow use that to actually extend this isomorphism for general F. And it turns out that this nth cohomology here, this isomorphism is represented by an explicit form like this, very canonical form, which is in fact invariant under a linear transformations of the projective space. Okay, so this, I mean, we just sketchily went over this last time, and since we don't have enough time, we'll move on. So now I want to talk about the Grothendieck duality. So first, let's start with the classical, the earlier version, which was due to Serre, which is the following: that if you start with a smooth projective scheme of dimension n over a field k, so by definition, smooth projective scheme means, again, it's some finite type, I mean, defined by finitely many polynomials over a polynomial ring, and I mean, more generally, it's obtained by as a closed immersion into projective space. So it's given by vanishing of some homogeneous polynomials, and so it's given by as a closed immersion in projective space. Closed immersion means that it's given by some ideal. I mean, it's the zero locus of some ideal, but we have to keep track of the ideal. So it's locally given by a graded ring model, the graded ring of Pn modulo some homogeneous ideal. And the extra assumption is that X is smooth over K, so it's non-singular. So this we didn't really go over too much, but you can imagine what it should look like. So it should look like a manifold. That's the idea. If it's smooth over K, one can show that the module of differentials has oops, this is wrong here. So just so module of differentials, one forms is locally free of rank n. So its nth exterior power can be taken, and that n is the dimension of X. So under that situation, the statement of Serre duality is the following. So we mentioned this last time. The dual of the ith cohomology of E over X, where E is a locally free sheaf of finite rank, is isomorphic to the n minus ith cohomology of E dual tensor with omega n. So this is Serre duality. And what we want to do is we want to give a general version of this, which will work over the derived categories. So to upgrade this, we will first realize what these objects are. So the object on the left, you can think of it as the ith homology of, sorry, so this is, wait a minute, yeah, this is the vector space dual. So you take Rf lower star, so simply push your locally free sheaf from here to here. So that pushing down is just the global sections functor. So you're just taking the ith derived functor of that and then taking its dual. And the other side here, again, we mentioned this last time. So instead of putting E dual, you can put E here, and then you are looking at n minus ith x between E and omega n. And this, the derived category version would be that, okay, so this is nothing but looking at the minus ith homology of this complex. And this complex is R Hom dot over K of Rf lower star E comma K. So R Hom dot is simply take this complex and just Hom it into this, and that's a new complex. But you have to do it, you're supposed to do it or by taking an injective resolution on this side, but it's over a field K. So actually you don't have to derive anything, simply just take Hom dot of Rf lower star E into K. And on this side, this x n minus I can be again interpreted as h minus I of R Hom dot of E into omega n. So this n here, I have brought it here. So I have shifted this by n. And again, so you're supposed to take an injective resolution of omega n, but instead shifted by n, and then do Hom dot. So Hom dot is simply the complex obtained by homing E into this complex. That will be your new complex. And apply its minus ith homology. That by definition will give you the x n minus I. So what we notice is that h minus I is common on both sides. So this is an isomorphism at the level of complexes, and that is really where derived categories was brought into picture by Grothendieck. So there's one more step we need to take. Here we are looking at complexes, and there's an isomorphism of complexes, but in fact we also need an alternative version which is equally useful, and that says that, okay, so I'll just quickly go over it, that whenever you are looking at, for example, instead of I, you could just take H naught of R Hom dot. So this is over any Y is any scheme or any topological space, whatever. So H naught R Hom dot OY F dot G dot is isomorphic to, by definition, H naught Hom dot OY F dot of an injective resolution of G dot. So you put I dot here. Injective resolutions exist, so I'm not going to bother about this point too much. Here we are. It's not just a sheaf here, it's a complex, but you can still find a quasi-isomorphism to a complex of injectives. Well, that's sort of the definition of injective resolution if G dot is what is called as bounded below. But in general, okay, one has to worry about a bit more. So it's something called K injective, like just like Shrikant talked about semi-projective. So one needs what is called as a K injective resolution. So we'll not worry about it. We'll just assume that, okay, there are so-called injective resolutions. And then H naught of Hom dot F dot I dot is by definition the zero cycles model of zero boundaries. But in this case, if you go through the definition of Hom dot of two complexes, so that's like a form a double complex out of this and put the obvious differentials with some minus signs and all that. If you go through that, then it will turn out that the zero cycles are nothing but chain maps, and boundaries are homotopy equivalences. These are the coming from the degree -1 things. And so this actually measures the homotopy maps between F dot to I dot, which then by definition of the derived category, I mean, you can go back here in the derived category, I dot and G dot are isomorphic. So this is the same as the derived category maps from F dot to G dot. So in the nutshell, finally, the conclusion is that we can say H naught R Hom dot F dot G dot is same as Hom. This is a group object, Hom in the derived category, F dot to G dot. Whereas here it was a complex, and then you were looking at the zeroth homology. Here it's just a set of all derived category morphisms between F dot and G dot. So it's so here it's H naught of a complex, however. So in general, if I put Hi here, then that's same as simply shift F by -I or G by +I here. And that also gives you, that follows immediately from this. So this is what we will need to get an alternate version. So here we had the complex version, which was R Hom dot of this here is isomorphic to R Hom dot. This is what we would like to say for extending Serre duality to give a slightly more general version of Serre duality, a derived version. And so now using this general fact here, we can we can phrase it like this. It's a set of all morphisms in the derived category from Rf lower star E to K is isomorphic to the set of all morphisms in the derived category from E to omega n x over K shifted by n. And E now we'll upgrade it. So initially we started with locally free, but in fact Grothendieck's version involves I mean pretty much any general thing. So Here it's a derived category of X, but maybe the only restriction is that it should the homology should be quasi-coherent. And perhaps later on, so in fact, I think this right now, such an isomorphism one can say is in fact true for all. But I mean, eventually we try to put some restrictions here. So maybe bounded above, bounded below, and that kind of thing. So that will come to later. So this is the version. So this is the Grothendieck's version of Sch duality. So you can write it like this, or equivalently, you can also just say that these two complexes are isomorphic. These are equivalent versions. So either these groups are isomorphic or the above complexes are isomorphic in the derived category. So then here is what we have as duality for smooth projective maps. Uh, I will try to give a sketch proof. So the general, so this is slightly general than what we have just stated above. So X and Y are now Noetherian, and instead of starting with a field or base ring, I'm now looking at any Noetherian scheme here. And this is what is called as a, okay, I forgot, okay, it's projective. It's a projective map, so which means that you can think of it as a closed immersion into this usual PM Y over Y. And we'll again assume that it's smooth. So that definition, again, I'll skip over that, but it's, you can intuitively see what it should mean. It's of relative dimension n. Then E belongs to DQCY. So E is a complex on Y with quasi-coherent homology. That's what it means. And we want, so the isomorphism, so the statement that we had just above here, we have just written the same thing, but instead of putting K here, because it was happening here, everything was over a field. Over a field, there are pretty much not many complexes you can write down. I mean, all complexes are direct sums of shifts of the field K itself, the copy of K itself. Whereas in general, you will have more complicated G here. So instead of putting K here, I have just put an arbitrary complex G. And so then for K, I had omega n x n. So now I will put LF upper star G and tensor with omega n x n. So that sort of generalizes this one. So this is Grothendieck's version. Hom dy Rf lower star Eg is isomorphic to Hom dx E LF upper star G tensor with omega n x n. And what does this mean? So in other words, this means I mean, essentially I have split this same statement into two statements. So first is that if you look at RF lower star, this functor, it sends, I mean, so it's, okay, it will send quasi-coherent modules. I mean, it will send complexes with quasi-coherent homology to complexes with quasi-coherent homology here. And so that functor has a right-adjoint. So that's what it's saying, because RF lower star is appearing here, and here there's some functor here. So this is the right-adjoint. So F cross, and this F cross, this right-adjoint is explicitly given by this formula here. I can drop the L's here and the L's here because F is in fact flat. This is a basic fact that smooth maps are in fact flat. So I can ignore the L here, and omega n is locally free, so that's also flat. So you can drop the L here. So I'll do that. And so this is F upper star G tensor with omega n x n. So that's what it means. So, so these are the two statements contained in this. And so this is what we want to prove. And this is how one proves it. This is pretty much how, for example, it is given in Hartshorne's textbook in algebraic geometry, though it's not a derived version, but it's the same idea. So for projective, relative projective space like this, one uses explicit calculations to check that this is right adjoint to this. So this is just based on interpreting those thing and upgrading it. We did it for, I mean, I just stated it or sketched it when Y is an affine scheme, Spec A, but essentially because of the way it is set up, one immediately extends it to, or one easily extends it to a more general scheme, and one can do a local calculation and then check that you get the same thing. So there the idea was that this is what, I mean, tensoring with this is what gives you the right adjoint. So if you interpret what we did, the explicit calculations we did, that's what it turns out to be, that this is the right adjoint. Now here is the interesting part. This seems like a rather silly case, or I would say maybe a degenerate case. So you take the closed immersion X to Y prime, X to projective space. That's a closed immersion. And even in this case, you try to find out the right adjoint to Ri lower star. Again, R I have dropped because in this case, I lower star will turn out to be exact, at least on quasi-core. Well, it's a closed immersion, yeah, it will turn out to be exact. And so Ri lower star, Ri lower star will, one can show it has a right adjoint, and at least over quasi-coherent modules, the right adjoint over the derived category with quasi-coherent homology is simply given by this formula here, which looks a bit complicated, but it just means that you are looking at sections. So R Hom, again, this should be R Hom dot. Dot. So R Hom dot OY prime of I lower star OX. So I lower star OX is OY prime modulo an ideal, because X is given by vanishing of some ideal. So this is just OY prime modulo an ideal, and you are mapping, you are replacing a complex, or let's start with the sheaf first, by Hom dot of OI prime modulo an ideal into that module. So you're essentially looking at sections which are supported along this closed subset X, or rather actually it's supported along the subscheme structure of X. So you have to be more precise, not just, I mean, it's a little, it's less than section supported along the closed subset, but it's more of section supported along the closed subscheme X. So those which are inherited by powers of, those which are inherited by exactly the ideal sheaf I and not higher powers of I. So that is what this is. And so it's if you had applied a single sheaf here and dropped the R, then that would just give you a subsheaf of sections supported along the closed subscheme X. So this is in general for a complex. You do it, you replace it by an injector resolution, and then therefore you have an R Hom dot here. And when you do that, this complex can be naturally restricted to X, so that you can apply I inverse functor, for example. At the level of homologies, it just means that there is no homology outside X, and all the homology is supported along X. So it's just restriction actually along the closed subset X. So this via a very elementary result, one can show that this is the right adjoint to Ri lower star. And that elementary result I refer to is nothing but Hom tensor adjointness. So if you use Hom tensor adjointness, you can show that this is the right adjoint to I lower star. So I have an explicit formula for I cross in this case also. So here I had an explicit formula for the smooth, for the projective case. And here for the closed immersion case, also I have an explicit formula. And this explicit formula can also be interpreted in a more convenient way in a special situation. That is when I is locally, so it's not just given by an ideal, but that ideal is locally given by regular sequences of length d over an open cover. So over each affine open cover, it's given by a regular sequence of length d. So it's local regular immersion of codimension d. And in that case, you can use some Koszul resolution of I lower star OX to prove that this same expression is nothing but Li upper star G tensored with this dth exterior power of I mod I square dual. So this is, let's see, I forget, it's the co-normal module perhaps of this embedding. And I mean, this is the top exterior power. Okay, so whatever. So this is the dth exterior power of that, and then there's a minus d. So you shifted d places to the right, where I is the ideal defining OY, I mean X and Y. So that is, so these are the two explicit expressions. And once we have these explicit expressions, we can actually come back here and prove this adjointness result by, I mean, we are looking for an adjoint. So we use the fact that if F is PI and I have an adjoint for this and I have an adjoint for this, then I just have an adjoint for both of them. I mean, just compose them. So that's the right adjoint to the composite of lower stars. Here it should be R, but since I lower star is going to be exact, I can drop the R here. So it's just the right adjoint to this. So I can find the right adjoint. And so therefore, that proves statement number one, that there is a right adjoint. And I proved it by simply factoring X into two special types of morphisms. And for each one of them, I had explicit formulas for the right adjoint, for closed immersion and for smooth. And the second thing is, if F is smooth, I want this right adjoint to have this explicit form In general, it's going to be complicated. If it is smooth, then it turns out that this I that this whenever you factor it like this I that you have has to be given by a regular immersion of codimension d, where d is m minus n, where m is the embedding dimension and n is the dimension of x over y. So d is m minus n, and so therefore in this case, if we actually if we use this formula, f cross is I cross p cross, so you will do I cross is in fact we have this explicit formula here, and p cross has this explicit formula here. So you put the two together, and what you get is f of a star, because you have p star and I star, and so you get f of a star. And you also have then you have this tensored with this, so that's what I've put here, and it is easy to see that this is actually omega n x over y n. So that is again some kind of determinants of coming from the okay, so you can write down one sequence, exact sequence, and from that it comes. So this is some explicit calculations, and one can show that this is just omega n. So this gives the other thing. So this is Grothendieck duality for projective maps. And I mean, this is just a sketch proof, but I hope you get the flavor for how it's done. But this is not enough. In fact, Grothendieck had a more elaborate theory, and we'll come to that shortly. And so to state that elaborate theory, first, let me recall what is a proper map. So first of all, projectives are, as I said earlier, are our analogs of compactifying affine things, but they are compactifying in a specific way. I mean, they are not the only quote unquote compact objects in algebraic geometry. So the actual definition is that of proper, which is analogous to what we know for locally compact spaces, Hausdorff locally compact spaces. So a map of Noetherian schemes is called proper if it's of finite type. So finite type is something I've been using here implicitly all the time, but it's always of finite type because it's given by finitely many variables here, followed by going modulo and ideal. So here in general, a map is called said to be finite type if you have, I mean, if you pick an affine open set here, an affine open set here, and the induced map of rings A to B is the finitely generated algebra map. So B is finitely generated over A. So that's finite type, and this is our implicit assumption. This will be our implicit assumption throughout. So throughout this lecture, whenever I'm talking about schemes, I'll be looking at Noetherian schemes which are of finite, and the maps will be of finite type. And so it's called proper if it is, in addition, universally closed. So universally closed means that X to Y sends closed sets to closed sets, but that would just be a closed map. So it's not just a closed map. Under base change also, it remains a closed map. So it sends closed sets to closed sets after a base change. So you map Y prime here and then look at X prime to Y prime. That also should be send closed sets to closed sets. So for Hausdorff locally compact topological spaces or maps between them, one can show that this is the same as the usual notion of proper maps. Inverse image of compact is compact. Here, however, keep in mind that we won't use the definition of inverse image of compact is compact because we are dealing with pathological topology. The Zariski topology on schemes is usually for that that's not the right thing to look at. So this is the right thing to look at. It's proper in this sense. So again, I will not spend more time on this. Just say that projective maps happen to be proper. So that is called elimination theory, and this can be proved. It requires a little bit of effort, and also this is another basic theorem that if over complex numbers, if you construct a finite type algebraic variety or scheme, then its complex valued points will automatically can be given a Euclidean topology, and then in that topology it has to be compact. So properness corresponds to compactness in that sense. And affine objects are rarely proper. In fact, they are proper if and only if they contain finitely many points. So affine objects are rarely proper. Projective objects are always proper, but there are more proper objects. Examples are slightly harder to give, so I'll skip over that. So Grothendieck duality, Grothendieck's point was, okay, so I have reached the end of my prepared notes, and so from now on I'll start writing notes. So Grothendieck's intention was to construct a theory which works for all maps, and in particular the adjointness statements holds for proper maps. So this is what I'll start talking about. So maybe this is a good time to pause for a minute. Are there any questions so far? I have not been looking at the chats. So any questions in the chats? Somebody has.
There's none there.
Oh, there's none. Okay, 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 fine. Okay, so let me go back. How do I remove this from the screen? Okay, never mind. Okay, so I'll start writing. Okay, so Grothendieck's. So here are the main things in Grothendieck duality theory. So this is a more elaborate theory designed to. So keep in mind that first it's designed to take care of proper maps, but it also asks the question of what is what do these objects look like when maps are not proper? What happens when you restrict these functors to open sets? I mean, what kind of things you get? So in fact, the idea is to in fact construct something which works for all maps. So therefore, let's see. So let SCH. So I will be very brief because now the speed will be slower for writing. So this is equal to category of finite type. So I'll just write FT separated. So this is again Hausdorff notion. So this is the algebraic geometry analog of Hausdorff. Our topologies are rarely Hausdorff in the usual sense. So the Hausdorff notion, which again I will not elaborate much, is just says that the diagonal map is closed. For topological spaces, one can easily see that a map is X is Hausdorff if and only if the diagonal is closed. So these maps, such maps, X to Y, of Noetherian schemes, So I'll take this category, and what Grothendieck duality does is to every F, so maybe I need X to Y in schemes. We want a map, we want a functor F Schrick DQC. Again, I'll put question mark here because we'll actually come back and clarify what the superscript. So superscript, so subscript QC, if you remember, is complexes which have quasi-coherent homology. Superscript will be how they are bounded. So bounded below, bounded above, that kind of thing. So in fact, maybe I should not keep it a secret. So just say that we will in fact insist that these be plus. So that turns out to work correctly. So plus means that so I use cochain indices. So all my indices are on the top and they are increasing as we go to the right. And so plus means that they exist in positive degrees. So they are 0 in sufficiently negative degrees. So I mean the homologies are all 0 in sufficiently negative degrees. So F Schrick such that first is so this Schrick is a pseudo functor. And this is a basic principle that we used above in the proof, that one should be able to compose what happens for two maps. So for example, if I have X to Y to Z, and if I have FG, then I should G Schrick, F Schrick should be, sorry, the other way. So I take GF Schrick. So if I want to, so first of all, I've changed the symbol a little bit. From cross, I've gone to Schrick, and I'll explain that shortly why. You'll see in the next remark. So whatever this functor is, GF Schrick, this should be isomorphic to F Schrick, G Schrick. So in other words, if I know it for these individual maps, then I should be able to cook it up for the usual map by, I mean, I should be able to compare them. So so this is what it is. So, but pseudo functor actually is a more elaborate definition. So a GF Schrick is isomorphic to this, and this is CFG. And in fact, this is a, so we'll call it, this is a comparison isomorphism, and this is associative vis-a-vis is associative, sorry, F comma G, associative for 3 maps. So for, so maybe I should not put this here. It's associative for X, Y, Z, W. So if you have 3 maps, then you can, I mean, I will not write the condition, but you can see that there has to be some obvious way of comparing things, and that diagram should commute. So I will not elaborate on that. So it's pseudo-functorial. And this is the, now here comes, here's why I introduced this new notation. And
so that commutation is supposed to be on the nose, okay?
Yes, on the nose, on the nose.
Hmm.
Yeah, it's associative for this, and it commutes on the nose. Yes. Yeah, thanks. F Sch Rc is in fact isomorphic to F cross for proper X to Y in C. And in fact, this is also pseudo-functorial. So, so if you have 2, so I will probably not say this more than this next time. So if you have 2 maps, then F cross F Sch Rc, G Sch Rc should be isomorphic to F cross, G cross, that kind of thing. So yeah,
it's equal to for smooth F or proper F. The
which one?
The line that you just wrote.
It's
point
for
number 2.
Proper.
Okay, but we have not defined F this cross for proper things. Earlier we did it only for smooth things, right?
Sorry, I should have done that. I didn't. Okay, point across. I didn't say somewhere here
it's
that
still proper. This is just projective smooth maps, right?
Okay, I always had in mind. Okay, thank you. So thanks. So I will just say then that for. Okay, thank you. So for a proper map, maybe I'll remove it here. So I think I forgot somewhere. Okay, so somewhere in my notes. So is isomorphic to, so let me just say the following, is the right adjoint. Okay, I'll just say that, just 1 minute. So proper F, where F cross is by definition right adjoint to Rf lower star. So in the previous case, everything was proper. So I was happily using F cross, but in general, my definition for right adjoint to Rf lower star will be F cross, even if it is not proper. So F cross will be my definition of right adjoint to Rf lower star. So I should have made that in the beginning, but sorry, I didn't say that. So this is my definition. And so let me come here. And now F Sch Rc is, so again, let me expand it and then I'll come back, is isomorphic to F star tensored with omega n for F X to Y smooth of relative dimension n in C. Not C, C is my category. So I meant whatever name I gave, SCH schemes. Again, this should be pseudo-functorial. And then the fourth one is what is called as base change. So maybe I should skip over this because otherwise I'll be going very slow. So, or maybe I'll just say what it is. Sorry. This is called flat base change. And I'll just say once. So here's a base change diagram. F is proper, and I'm taking fiber product with so this proper map of fiber product with flat map. So if you call this as V and this as G, then the base change isomorphism says that I should have something like this. And there are some further conditions, some obvious ones coming from here. So here U is flat, U comma V are flat, and F comma G proper. Okay, so so what I'm saying is that one constructs a pseudo-functor, but it's not exactly, so this is the point, it's not exactly equal to the right adjoint to Rf lower star. When we were dealing with projective situation, everything was, all the maps were proper. So we were simply worrying about the right adjoint, but in general, that's not what it is. I want to localize and I want to go local. And if I want to go local, I should be able to say what it is for non-proper maps also. So for non-proper maps, this is what I will insist, that F sh be isomorphic to this. And the basic technique for going non-local is this flat base change. So this flat base change isomorphism theorem is useful because it's sort of, I mean, given something here, you may have a right adjoint here, but we are now, for example, this is called open base change. You can, for example, look at an open subset here.
Snake, what is a conclusion of 4? What is beta supposed to be? Just
there's isomorphism.
And you're only, the input is F and U is flat, F is proper, right?
U is, yeah, U and V are flat, F and G are proper. This is a fiber product. So if U is flat and F is proper, you get the other two. And what we want is that we want this isomorphism. This is called flat base change isomorphism. So there's a flat base. So in other words, Sch Rc is compatible with flat base change. So these are the requirements. And in fact, Grothendieck's theorem, well, I mean, this is what Grothendieck, I think, had in mind, but it took a while to prove this. So now we have a theory which gives a proof of this. So there's a theorem. I won't state it formally, but essentially I mean, above Sch Rc on schemes exists. And I will just briefly say what are the main points or main inputs. So see, I'm trying to construct, but I went, so when we talked about the projective situation, we were concentrating on the right adjoint. But now we are trying to say, we are trying to define F for every map. And so that may not be proper. So if it is not proper, then you can't expect it to be right adjoint. In fact, we don't want it to be right adjoint. What we want is, for example, if it is smooth, it should look like this. At the same time, it should be pseudo-functorial. And so if you can compose two maps, it should, I mean, you should be able to give what it is. So therefore, here's one way of constructing a theory of F upper Sch Rc, of upper Sch Rc. So one uses, so there's something called Nagata compactification. Again, maybe I should cut down time. I will not say what it is, just write it in words maybe, or in symbols. So you start with a map fx to y in schemes. Then it factors, so f factors as maybe I'll call it x bar and y, where this is proper, okay, sorry, f bar. So this is proper, and this is open immersion. F is equal to f bar composed with I. So this is called as compactification. If y was a point, if y is a point, then this is just saying that I have something proper. I mean, I have a proper variety, I have a compact variety, so to speak, and X is an open subset of that. So I'm saying that any variety can be compactified. This is not so obvious because our varieties are not necessarily affine. So this is quite a subtle result. Okay, let me not say more about it. Now, so set F Sch Rc to be equal to f bar cross. So I'll come to what this is. So and then I upper star. So this is this is our plan. So notice, for example, here that I is open immersion. So in particular, it's smooth, but it's smooth of relative dimension 0. So this is like saying I am looking at I upper star tensored with omega 0, which is just doing nothing. So this is just I upper star. And this is our right adjoint. So first I need to say why this exists. So in this generality. So the theorem again. So theorem is that F proper implies, or okay, you don't need F proper actually. So for any F in C, sorry, C is what I originally wrote, and then I, oops, schemes, RF lower star has a right adjoint. Again, I am not writing the derived categories in the picture. So this theorem is, well, it was originally proved by Deligne in the 1960s, and then later on also by Niemann using Brown representability. So Niemann used what is called as a, Deligne used what is called as a special adjoint functor theorem, and Niemann used some ideas from Brown representability to prove this theorem. So so therefore, this F bar cross exists. And now I have I upper star. That is, so what does it mean? Sorry, what am I saying? I have written the other way. It should be the other way. I upper star F bar cross. Never mind. So in other words, if you want to construct F upper shriek, start with a complex here. You want to construct a complex here, F upper shriek of F. So what we are saying is that first construct it here, just by looking at the right adjoint of RF bar lower star, and then restrict it. Upper star is just restricting it. So simply restrict it. And now the long and elaborate part is that check that shriek is a pseudo functor. So you can check this in, you can, for example, find it in Lipman's book. And flat base change theorem holds. So flat base change holds for shriek. In fact, it's enough to check it for cross because for star it automatically holds. So then you can put the two together. And you also need to check finally that see, our requirement was that if f x to y is smooth of relative dimension n, then f shriek is isomorphic to f upper star tensored with omega n x over y of n shifted by n. So it's not obvious that this will happen, meaning that, I mean, just from the formula, it's not clear, because what we are saying, look at the formula. The formula is saying that you just compactify your map and then look at some abstractly constructed right adjoint and then simply restrict it to the open immersion, open set. So therefore, it's not at all obvious that if it is smooth, it should give this. But one can prove this, and this is due to Verdier. And in fact, I had a plan of presenting this, but I think it will take so much time that I will skip this. So
I guess one of the problems, sorry, Snake, one of the issues here is that there is no canonical or functorial compactification, right? Because you've chosen the compactification.
Yeah, yeah, thank you. So what Shrikant is pointing out is that this compactification is hardly unique. So there may be, for example, even for A1, you can, sorry, A2, for instance, you can compactify it as P1 cross P1, or you can compactify it as P2. So I mean, just in this situation, you have so many compactifications, but in general, in fact, you have plenty, infinitely many compactifications. In fact, here also you can start blowing up and you can do all sorts of things. So in general, there are lots and lots of compactifications, and it's not at all obvious that this formula will actually is in fact, I mean, it's unique, meaning it's unique up to isomorphism. And that's where the flat base change comes in. Open base change and flat base change. Open base change is a special case of flat base change. And it's using this, one can actually show that given two compactifications, you can sort of compare them and find a dominating compactification, and then show that this formula is independent of the factorization. So that also needs to be checked. But all that is part of checking that it's a pseudo functor.
Can I ask one question?
Yeah, sure.
So when you were setting up what we wanted out of this stuff in the in an earlier slide, you said F upper Schrick should be F cross, where F cross is the right adjoint for proper F. Right?
Okay.
Here. And I just wanted to I'm just asking for a clarification.
Yeah.
But what you wrote now is that F upper Schrick is a right adjoint in the category as schemes itself, not just for proper morphisms.
F upper Schrick is not right adjoint. F cross is right adjoint.
Here, but in the later slide.
No, I have not said anywhere.
Delhi-Neiman theorem.
Proper.
No, it has a right adjoint. I only said it has a right adjoint, and that is what goes into construct. I mean, that's how I get this. I'm saying RF lower star has a right adjoint. Let me call it F cross.
That F cross is done only for this F bar, the compact.
Yeah. So okay, if you want, but in fact,
okay, fine.
Yeah. So okay, what I can do is I can call this G.
So F cross is the wrong thing for non-proper maps.
Yeah. So the point is that the cross is the wrong thing for maps. For non-proper maps, I'm not interested in the right adjoint. I am actually I'm interested in something else, and that something else, for example, for smooth maps should be like this, which will not be right adjoint. If you have, for example, an affine smooth map, this will not be right adjoint.
Yeah.
So that is what I mean.
Yeah. Thanks.
So okay, so that is one thing. Yeah. Okay. So now I had 2-3 pages. Let's see, how much can I really do? I have 10. So I'll take a few more minutes. So a few remarks, and then I wanted to go say a little bit about Verdier duality also, which is okay. So let's see. So the other remark now I want to say, I won't go too much into this. So there was an earlier approach of Grothendieck, which constructed just a few remarks about earlier approach. Which is somewhat different, and what it does is you actually embed it. You factor your map F in a slightly different way. So this is your F, and now we factor it like this, where this is closed immersion, not open, and this is smooth. Again, of relative dimension n. And in this case, you look at what are the expected formulas for H-Rc and I-Rc. So the expected formulas are H-Rc should be H upper star tensored with omega n z over y. And I is a closed immersion, and we saw when we looked at projective morphisms that I-Rc should be I inverse of R Hom dot Rfrom, let's see, in this case it's OZ of I lower star OX, which is just OZ modulo and ideal into this. So these are the expected formulas, and for duality. I mean, this is actually just the right adjoint to Ri lower star. This is not the right adjoint to H lower star again, but this is the expected formula. This is, oh sorry, there is a n here. This is the expected formula for H-Rc. So these are the explicit formulas, and so therefore what you would like to do is F-Rc is equal to so which one? H-Rc you apply first, and then I-Rc. You want to go from here. You want to go from here to here, and then from here to here. So given a complex, you apply H-Rc and then you apply I-Rc. The I-Rc case is you are just looking at right adjoint to Ri lower star, but here it is not the right adjoint. So this is what you would like to do, and it works it worked for projective maps, and that's what we did here, X to projective space to Y. But in general, you don't have, for an arbitrary finite type map, you don't have such a factorization. And so therefore, since you don't have such a factorization, Grothendieck came up with suggested a different approach, which is no longer used because it has some, it's a slightly more complicated approach, but it has something interesting coming out of it. One thing was that you can always locally factor such maps. So any map from X to Y can be locally factored because you just take affine piece here, and then it's just polynomial ring, modulo, and ideal. So any map can be locally factored like this. So locally you can construct upper Schrick, but in the derived category, you can't glue complexes over an open cover. So therefore, you can't globally do it. And so Grothendieck's approach to globally doing it was very complicated. But one of the things that he used in that process, which I'll now very briefly mention because it's worth saying here, is that, okay, so let's start with, again, X to spec K. So now we are looking at a variety over a field K, or a scheme over a field K. And the question is, what does F upper Schrick K look like? So whatever theory of F upper Schrick you come up with, so here field K is a field. So when X is smooth of relative dimension n, I've been saying it several times, so then we know that F upper Schrick K is omega nx shifted by n. But what if X is not smooth? So if X has a singularity, and here's a typical example. So for example, take a line passing through a plane, and they intersect here. Then in this case, you can intuitively guess that, look, F upper Schrick K is what will give you, in this case, things are not proper, but suppose that I had added enough points at infinity. So this was a projective plane and a projective line, if you like. Then I know that F upper Schrick K, to give me duality, for sheaves supported purely along this line, I would need omega of this line shifted by 1. But for this plane, I would need omega shifted by 2 for this plane, for sheaves supported only along the plane. So in general, F upper Schrick K should work for all sorts of sheaves supported along this entire thing. And so that will create problems. And so we can see that therefore it will have, that sort of is a heuristic argument to say that this has homology in degrees -2 and -1, both. -1 because of the line and -2 because of the plane. So this is an example of a singularity for which F upper Schrick K is. So here, in the previous example, F upper Schrick K was sitting only in 1 degree, and that was when it was smooth. But here, F upper Schrick K is actually a complex. So this is what is called as a non-Cohen-Macaulay singularity, and in this case, F upper Schrick K is just a complex. So F upper Schrick K has the following property. It is what is called as a dualizing complex. So D dot belonging to derived category with coherent homology is called dualizing. Sorry, I'm going to take a few minutes. Is that okay?
Yeah, sure, Suresh, carry on.
Let me just finish what I wanted to say.
Yeah.
It's called dualizing. Okay, so if there's one technical condition that it has a finite injective dimension, so let me not emphasize this. So finite injective dimension, it's actually an important condition, but we'll not go over it. So, and for all F belonging to DCX, there's an auto duality. So F goes to R Hom dot OX, and then again R Hom dot OX FD D is an isomorphism in the derived category. So what is this? This is saying that you dualize F with respect to F twice. So the double dual of F with respect to this D is actually is isomorphic to F, again in the derived category, of course. And so one can check. So this is called auto duality. And one can check, for example, that if A is a regular scheme, then A shifted in any degree M is dualizing, the dualizing complex. And here's the interesting part. If X to Y is finite type, so for example, map between varieties or schemes, and D is dualizing, on Y, then that implies f upper Schrick D is dualizing on X. You can check this. You can prove this by factoring f by checking this locally and factoring f into closed immersions and smooth maps, and then use explicit formulas. So that's one way of proving it. So it's not hard to prove. And here's a basic observation by Grothendieck, or it's there in H-RHom's book, for example, is that in fact f upper Schrick f in this case. So again, here f belongs to dc of x. So unfortunately, this theory requires you to work with coherent homology. So this is the slight drawback. Yeah. So then this is isomorphic to double dual. So R Hom dot OX, sorry, LF upper star. No, where am I putting LF upper star? Yeah, LF upper star. R Hom dot OY FD into F Schrick D. So what this is saying, so this big looking formula is saying that if you want to compute F Schrick F, that mysterious functor, which is right adjoint on proper and open immersions, it's star, or for smooth maps, it's F upper star tensor with omega. Here's what you can do. Take, dualize it on Y. Sorry, this is Y here. I mean, it's meant to be Y, but it is not looking like Y. So dualize it on Y, pull it back just using ordinary F upper star, and dualize it back on X, because F upper Schrick D is dualizing on X. So dualize it on back on X, but using this complex. And Grothendieck's earlier approach to F upper Schrick, therefore, was based on the fact that for dualizing complexes, somehow gluing holds in a certain sense. And so given D, one should be able to construct F upper Schrick D in a nice way. I mean, in a pseudo-functorial way, so to speak. And once you have that, then one should be able to define F Schrick like this, and then hope that this will do the job in general. The drawback is that it's a more lengthy and more complicated approach, less transparent, and it also puts the condition of F having coherent homology. And so a priori, it's not clear how to remove this. Because somehow double dualizing is involved everywhere, and every time double dualizing is involved, you have to assume everything is coherent. So this was this is how his approach was, and but it involved a lot of complications. So final remarks. Sorry, I'll just take 5 more minutes and then I'll stop. Sorry, this is my last lecture, so I hope a little bit of delay is okay. So a few remarks I wanted to say. Some things I'll maybe say orally. One is that if you look at this dualizing complex that I mentioned, which comes up naturally for varieties, which is F upper Schrick K. This dualizing complex in general has lots of homologies, but its top homology means leftmost homology. So that will occur in dimension minus n, where n is the in degree minus n, where n is the dimension of x. So in this case, for example, -2. So its topmost homology is called the dualizing sheaf or dualizing module. And it exists even if x is not proper. If x is proper, it will give you what is called as a 0th level duality. It's the simplest duality, but it doesn't give you the full duality theorem. For the full duality theorem, you need the dualizing complex. That's number one. And X is called Cohen-Macaulay if you have F upper Schrick K, it has only one homology, and that is sitting in the minus n, like for example for smooth. So smooth is a very special case of Cohen-Macaulay. So I shouldn't say F is called Cohen-Macaulay. I mean, there's a different definition for Cohen-Macaulay singularities, but X is Cohen-Macaulay if and only if F upper Schrick K has only one homology, and that is sitting in degree n. And F is Gorenstein if and only if it's Cohen-Macaulay, so it has only one homology. So it won't have two homologies like this, or it won't have non-equidimensional components like this. So it's Cohen-Macaulay. And moreover, this the only sole existing homology, the so-called dualizing module, is invertible. So those are definitions, but these are I mean, these are of great interest for people working in singularity theory and commutative algebra. But right now I'll skip over that and just mention a few remarks on Verdier duality, just few minutes, and then I'll stop. So which is analogous to this. So sorry, I need it to be, I guess I don't have that much time. So f x to y continuous map of locally compact spaces, Hausdorff spaces. And what one defines is f lower Schrick. And unfortunately, this in algebraic geometry, we don't have a good notion for this because it doesn't take quasi-coherent to quasi-coherent. So it takes sheaves on x to sheaves on y. And what does it do? So it take a sheaf f here, then f lower Schrick f. This is called direct image with compact support. So for any open subset V of y, this gives you sections in, oops, f inverse V to, oh my battery is going down. Support of S to Y is proper. So this is a subsheaf of the direct image, and it's called direct image with proper supports. With proper supports. And the main theorem is, so this is Verdier duality, is that, so Verdier duality, the following theorem. So here I'll have to make a small assumption. If, oops, why does this happen? Okay. If Rf lower star, Rf lower Schrick, so take the right derived functor of f lower Schrick. If this has finite cohomological, so we'll have to assume it has some what is called as finite cohomological dimension. So this is a technical condition. Let's ignore this. For manifolds for submersions, etc., it's automatically there. Then this implies Rf lower Schrick has a right-adjoint. And this right-adjoint, we are not saying f lower Schrick has a right-adjoint. We are saying Rf lower Schrick has a right-adjoint, and this is so this is a derived version. In fact, one can argue that f lower Schrick expecting right-adjoint for that is too strong, and it will fail. And so the statement is that this is Hom Rf lower Schrick f g is isomorphic, and so this is in the derived category over. So where is this y? And then Hom derived category over x f Schrick g. So one can view this as some version of some generalization of Poincaré duality. For example, what was f? Sorry, f is x to y, and yeah, that's where this Rf lower Schrick has a finite cohomological dimension assumption comes in. So this is our map of locally compact topological spaces. And to view this as a generalization of Serre duality, sorry, not Serre, Verdier duality, Poincaré duality, think of y as a point, and think of f g also. So let's see, g also. So y is a point, g is some free. So on a point, what can you get? The sheaf is just given by any group. So put a field there. Your favorite field may be Q or real numbers or complex numbers. Then this is just taking global sections, maybe with compact support. So this is just looking at the cohomology of, and put f is equal to constant sheaf. So put f is equal to maybe ry, rx, and g is equal to ry. So these are constant sheaves. And maybe put y is equal to point. So if you make these three assumptions, then you will see that what you're getting is Poincaré duality. Because this is Rf lower Schrick is simply taking cohomology of the constant sheaf. So that is your singular cohomology. And this is the dual of that. And here, okay, you need one more thing. So we need, so this implies f upper shriek g is isomorphic to Rx shifted by n if X is n-dimensional manifold. Orientable. And if it's not orientable, then you have to replace Rx by the orientation sheaf. So in general, this is what you'll get, and this will give you Poincaré duality. So I don't know, I don't want to elaborate on this further. So I'll stop here. So sorry about that. This is the best I could do. Thank you.